Have you ever really, truly thought about what happens when you hit the send button? I mean, really thought about it? Well, today we're going to do just that. We're going on an absolutely incredible journey, following a single bit of data as it zips across the world. Right. So you're there, you've typed out your message, maybe attached a photo, and you click send. And poof, it's gone. It feels completely instant, almost like magic, doesn't it? But what is actually happening in that tiny sliver of a second? Let's peel back the curtain and trace the wild journey of just one tiny bit of your information. Okay, so our story starts with a really basic problem, right? Your computer or your phone needs to send a message to another device, and that device could be on the other side of the planet. So how in the world does it cross that massive distance? Well, this diagram pretty much shows the classic setup. On the left, that's your computer. It's got the data, but it can't just, yell it out into the void and hope for the best. Nope. It needs a special kind of translator to connect to the outside world. And that translator? That's the box on the right, the modem. So right off the bat, we hit our first major hurdle, and it's basically a language barrier. See, your computer thinks in digital. It's all crisp, clean ones and zeros, these sharp little pulses. But the long-distance lines, like the old telephone wires that still make up parts of the internet, they were built for sound. They speak analog, smooth, wavy signals. They're two different languages. And the solution to this translation problem is a process called modulation. You could think of it as the art of taking that sharp, blocky digital information and cleverly encoding it onto a smooth analog wave, a wave that can actually survive the long trip ahead. And this image just illustrates that modem's job perfectly. Check out the left side. Those are your computer's digital bits, right? A clear series of on-off pulses. The first modem takes that and masterfully transforms it into that smooth, continuous analog wave you see in the middle. That wave is what actually travels down the line. Then, at the other end, a second modem catches it and translates it perfectly back into the original digital pulses for the receiving computer. It's kind of like translating a book into a song, sending the song, and then having someone on the other end turn it back into the exact same book. It's brilliant. Now, how do we actually send these bits? You'd think, hey, let's just send them all at once, in parallel, like on the left. That's got to be fastest, right? And for super short distances, like inside your computer, you'd be correct. But over long distances, oh man, it becomes a total nightmare trying to keep all those different lanes perfectly synchronized. So for the long haul, we do it single file. We send them one by one in what we call a serial transmission. It might seem slower, but trust me, it's way, way more reliable. So our little analog signal is now on its way. But the transmission line is not some quiet, pristine superhighway. Oh no, it is a perilous path, and it is full of dangers that are constantly threatening to mess up our data at every single turn. Our signal is up against three main enemies out there. First up is attenuation. Just like when you shout, your voice fades over a distance, the signal gets weaker the farther it goes. Second is distortion. The wire itself can actually warp the signal shape, kind of like a funhouse mirror. And finally, there's noise. Just random electrical interference that acts like static on a radio, scrambling the message. And here's the absolute crucial takeaway from all this. The signal that arrives is never a perfect copy of the one that was sent. Ever. Okay, so if errors are pretty much guaranteed to happen, how does anything on the internet ever work? I mean, really. This is where some unbelievably clever engineering comes into play. We basically need a spell checker, but for bits. The main idea here is something called redundancy. We know we can't prevent every error, but we can definitely prepare for them. And to do that, we intentionally add extra, non-essential bits into our message. We call these check bits, and their one and only job is to help the receiver figure out if the original data got messed up along the way. Now, this whole redundancy thing can work in two main ways. The simpler version is error detection. Think of this like a smoke alarm. It doesn't put out the fire, it just screams at you that something is wrong. Then you have the more advanced version, error correction. This is like a fire sprinkler system. It doesn't just know there's a problem, it has enough information built in to fix it right there on the spot. So, what does a simple check look like? Well, the most basic one is called the parity bit. It's super simple. Before sending a chunk of bits, the sender just counts up the number of ones. Then it adds one extra bit, either a 0 or a 1, just to make the total number of ones either even or odd. The receiver does the exact same count. If the final count doesn't match what it was expecting, bam, it knows an error happened somewhere. Simple, right? But it works. But just knowing an error happened isn't always good enough. Sometimes you need to fix it right away without having to ask the sender to send it all over again. So, what if you could add just enough check bits to not only detect an error, but to pinpoint its exact location? Well, for that, we turn to a brilliant solution: Hamming codes. This is the logic behind a Hamming code. Now, don't worry about all the math on the screen. Let's just focus on the magic. By adding just a few of these clever check bits, the receiver can run a series of tests on the data it gets. If a test fails, the result isn't just a generic error message. It's the literal address of the corrupted bit. It can find that one bad bit and flip it back to what it's supposed to be. It's basically a self-correcting message. How cool is that? All right, so our data has been translated, it's been sent, it's survived the noisy journey, and it's even been corrected. It arrived safe and sound. But this brings up a whole new question. Just how fast can all of this happen? Is there like a physical speed limit for our data? Okay, to get a handle on speed, think of it this way. The baud rate is how many cars pass a certain point on a highway every second. The bit rate is how many people pass that point. Now look at the image on the left. Each car has one person, so the number of cars equals the number of people. Simple. But on the right, we figured out how to cram 2 people into each car. The number of cars per second, the baud rate, hasn't changed, but we've doubled the number of people getting through. That's the difference between baud rate and bit rate. So the first speed limit was figured out by a guy named Harry Nyquist. His theorem sets the absolute maximum baud rate, the max number of cars per second, on a perfect, totally noise-free channel. It's a theoretical limit that's dictated purely by the channel's bandwidth, which you can think of as how many lanes the highway has. But, as we've already established, our channels are not perfect. They're noisy. So another genius, Claude Shannon, came along and gave us the second, much more realistic speed limit. Shannon's theorem defines the maximum bit rate, the number of people, by taking into account both the bandwidth, which is the width of the highway, and the signal-to-noise ratio, which is kind of like how foggy it is on that highway. This is the true, unbreakable speed limit for any communication channel in the real world. So when you really stop and think about it, hitting send is anything but simple. It's this incredibly fast ballet of translation from digital to analog, a brutal fight for survival against all that noise and distortion, and this amazing process of self-verification and correction. And it's all happening within the fundamental speed limits set by the laws of physics. We've just followed the incredible journey of a single message. But what happens when billions of these journeys are all happening at the exact same moment, crisscrossing the entire globe? Well, that incredibly complex dance, that is a story for another time. Thanks for watching.